Hello again, physics friends. We're going to do a couple quick examples on how to calculate the center of mass for discrete objects, in other words, collections of point particles. We'll start by making sure we understand what the center of mass equation says. In particular, it's a vector equation, so we want to make sure we understand how to interpret it in terms of the components of that vector. So here we have the definition of the center of mass for a collection of two point particles, m1 and m2, and if we let capital M be the sum of m1 and m2, in other words, capital M is the total mass of the system, then we can write this out as m1 times the x and y coordinate of object 1 plus m2 times the position vector to object 2 divided by the total mass of the system. And so when we combine this all together, we basically get m1 x1 plus m2 x2 in the x direction, and m1 y1 plus m2 y2 in the y direction, all over m. So this is a vector equation that you can break out into two separate equations. And those two equations would be easily identified if we think about the position of the center of mass as the x and y coordinates of the center of mass. Then we get two equations, one in the x direction and one in the y direction. So in the x direction, we have the x center of mass is m1 x1 plus m2 x2 over the total mass. And in the y direction, we have the y center of mass coordinate is m1 y1 plus m2 y2 over the total mass. Okay, so this vector equation is basically encoding two separate equations, one for each direction, the x direction and the y direction. Okay, so let's do a couple of example problems here. I'll shrink that to give myself a little extra space. And here we will say, let's start with a 1D problem. And let's say we have the following setup. In the x direction, let's say we have a mass 4 meters from the origin and a mass 10 meters from the origin. Okay, so we have m1 and we have m2. And let's let m2 be 15 kilograms and m1 be 5 kilograms. Okay, so in this case, there's only the x center of mass because both objects are on the x-axis, so the y center of mass will be 0. The x center of mass would be m1 x1 plus m2 x2 divided by the total mass. m1 is 5 kilograms. x1 is 4 meters, m2 is 15 kilograms, and it's 10 meters from the origin, and we have a total of 20 kilograms. So up top we have 20 plus 150, that's 170. And in the denominator we have 20 kilograms. Kilograms cancel, and we're left with 17 over 2, or 8.5 meters. So if we count this off, 5, 6, 7, 8, 9, the center of mass is midway between 8 and 9. So it's right there at 8.5 meters away from the origin. As a reality check, we know that the center of mass is basically where you could put a pivot to balance the system. Okay, so one way to kind of see this visually is to draw out our two masses. Okay, we have a 5 kilogram object and we have our 15 kilogram object. And if we imagine connecting them with a massless rod, but one that's rigid, we have to put a pivot here somewhere that balances So the system is balanced. And so that position better, I'll draw my center of mass symbol as this little crisscross shape. And then the question is, how can I think about this? Well, I know that my heavier mass is 3 times heavier than my lighter mass. So that means I need my my distance from the pivot to the heavier mass to be, let's say, 1 unit. And then I need the distance from the pivot to the lighter mass to be 3 times as large. Okay. We also know that the first mass is located at x equals 4 meters and the second at x equals 10 meters. So that's a total separation of 6 meters. So that tells me that 3x plus x is equal to 6 meters. So 4x is equal to 6 meters. That means x is equal to 1.5 meters. That means my pivot point has to be 1.5 meters away from my heavier object. So if I start at 10 and I count over 1.5 meters to the left, I'm going to be at 8.5 meters, which matches my other calculation. So that all checks out. For our second example, and this will be our last one, this is a quick video, let's consider a 2D system. So we'll have 2 masses on the x-axis, but then a third mass off of the x-axis. And let's just have them in proportion of 1m, 1m, and 2m. And in terms of separations, let's say the vertical separation is a distance of L, whereas the horizontal separation here is 2L. Okay, and we want to find the center of mass of the system. So let's label these as numbers that we can just refer to them by. So we'll call them 1, 2, and 3, and we can identify the position vectors to each of these objects, R1, R2, and R3. R1 is going to be 0, 0. That object is right at the origin. R2 is at a distance 2L in the x direction and 0 in the y direction. And R3 is at the same 2L, but it's also offset in y. Okay, and so now all we really need to know, the other thing we should add is also the total mass is 2m plus m plus m, or 4m. So the total mass of the system is 4. So the x center of mass coordinate is equal to x1 times m1, x2 times m2, plus x3 times m3, all divided by the total mass. So x1, x2, and x3 are all read off from our vector representation. So it's 0 times 2m plus 2l times 1m plus 2l times 1m, all over a total of 4 little m. So when we add that up on the top, we're going to get 2ml plus 2ml is 4ml divided by 4m, which is simply L. Okay, so before we go on, let's just make sure that makes sense. If you take all of the masses and project them down onto the x-axis, you're going to have 2m at the origin, and you're going to have 2m a distance 2l away from the origin. So you have equal masses at those two places, and so you'd expect the center of mass to be midway between, which is 1l, and that's exactly what we see. So that answer is sensible. How about in the y direction? In the y direction, well, maybe we can talk through it before we do a calculation. We have 1m up here. If we project everything onto the y-axis, we have 1m up here, and we have 3m down here. So we're going to expect the center of mass to be closer to the origin than it is to y equals L. So let's see how that plays out. The y center of mass is y1 times m1, y2 times m2, plus y3 times m3, divided by the total mass. But notice that two of our masses are at y equals 0. So that simplifies things. y1 is 0 and y2 is 0. So y3 is at a height L, and the mass of that object is 1m. And we divide that by total mass of the system. We get a little cancellation, and indeed, we find that the center of mass in the y direction is at a coordinate L over 4. So we can draw in the location of the center of mass. If this is a distance L, and this would be L over 2, so L over 4 would be around here. So our center of mass lies in the y direction at that line, and it lies in the x direction on this line. So our center of mass is at this location right here. Good. So those are just two real quick examples of how to calculate the center of mass. Of course, lots of systems are not going to be composed of point particles, but rather maybe continuous objects, such as a sheet or a plane of material or something like that. And so if you then want to compute the center of mass of that continuous object, you'll need to do, instead of a sum, you'll need to extend that to an integral. So you'll have basically an infinite number of chunks of material. Each one of those chunks will have a position vector. Let's say like this, r sub I, and then we have to add up all of the masses and locations, the weighted average basically of all of the masses at the positions to get the center of mass of the whole object, and that will involve an integral. But today we're just focused on discrete point particle systems, and we've done an example in 1D and an example in 2D. So we're going to stop there for now, and until next time, take care and be well.